Hello, everyone. We're going to get started now. Thank you for joining the webinar today. My name is Ken Sloat, and I am an R&D and technical sales engineer on Variscite's embedded software engineering team. Today, I'm going to be talking to you about enhancing your embedded software design with Docker. So first, let's go over the agenda today. I'm going to start by talking a little bit about Variscite, who we are, what we do. Next, follow up just a basic explanation about Docker, followed by some Docker basics, so kind of how Docker containers work. Following to that, I will talk about host-based containers and then embedded device-based containers, and I'll explain what I mean by that when I get to those portions. Following that, talk a little bit about Variscite's Docker Advantage, as well as touching on just a couple of advanced topics with Docker. Finally, there will be a live Q&A session at the end. So I encourage you all throughout the presentation, there should be a little question box somewhere in the webinar where you can enter a question if you think about it. So if you do those ahead of time, it'll give us some more time to take a look at those, so maybe we can address them live at the end. Keep in mind this entire presentation will be recorded, so if you miss something, don't worry, because this presentation will be uploaded to our website, the video and all. So with that, let's get started. So a little bit about Variscite. Variscite is a leading system on module provider with 20 years in the SOM market and has an extensive customer base and pipeline. While many other SOM vendors use contract manufacturing facilities, we own our own state-of-the-art PCBA production facilities. This ensures that we have complete control over the manufacturing process, which is very important, especially with recent industry-wide supply chain shortage and sourcing issues. We are also an NXP Platinum partner, which allows us better lead times, as well as early access to NXP parts, software, and tools. In that role, we also provide the most diversified i.MX-based product portfolio available to date. Our highest quality standards meet even the strictest regulatory requirements, including medical ISO 13485-2016 standard, and we are also ISO 9001-2015 and ISO 14001-2015 certified. Additionally, we have an ecosystem of design partners in order to offer a complete end-to-end solution for our customers. So at Variscite, we offer several key advantages with our SoMs. To start, most of our SoMs fall into two major families, the Dart and Var SOM families. And within these families, the members are generally pin-to-pin compatible. I'll talk more about that later in the presentation. While other SOM vendors might only stock 3 or 4 variants of a SOM, we actually offer the ability with any of our SOMs to fully customize individual features like memory size, CPU core count, and other various on-SOM peripherals. Our 100% yield performance ensures that everything is tested and validated before reaching a customer. So our customers can rest assured that the SOMs they receive will be high quality and fully functional. Additionally, we provide production-ready hardware and software that has been tested and used by hundreds of customers to date. So it has proven high reliability and low risk. This, coupled with the free support we offer, allows our customers to accelerate their path to production. With robust longevity of up to 15 years on our SOMs, our customers can rest assured that we can continue to supply them throughout the life cycle of their product. So next, I'm going to talk a little bit about what Docker is. So what is Docker? Well, a basic definition, Docker is a kind of system that provides OS-level virtualization. However, it does so using a set of what they call containers that contain all needed dependencies to run an application. So Docker containers also provide a level of isolation between applications. And we're going to talk a little bit more about virtualization on the next slide. So a virtual machine is a virtualized computer system, essentially. It usually is a software mechanism, and sometimes there's underlying hardware support that allows a system to essentially imitate another system. So a virtual machine might, for example, allow you to run a Linux operating system within Windows, like run Ubuntu on your Windows machine. The software that runs a virtual machine is often referred to as a hypervisor. For example, you've probably heard of Oracle VirtualBox or Hyper-V or VMware, and there's different types of hypervisors, but we're not going to get to that level of detail here for the Docker presentation. So I'm talking about virtual machines. Is Docker a virtual machine? Well, not exactly, but Docker has similarities to VMs. So Docker does use virtualization to provide containers. You could kind of think of these containers like individual virtual machines. However, unlike a traditional virtual machine, they all share the same underlying virtual Linux kernel. So this particular design paradigm allows for containers to be much lighter weight and flexible than traditional VMs. You can imagine if you had multiple instances of VirtualBox running, it's going to consume a lot of resources. So due to this Docker's lightweight design, multiple services could be spun up potentially in individual containers on one system with minimized overhead. So why would you want to use containers? Well, we're going to get into specific embedded software use cases, but I just want to give some kind of more high-level reasons, advantages of Docker. So first of all, containers provide a consistent runtime environment for an application. As software engineers, we've probably all uttered the phrase, well, it runs on my machine. Containers allow services to be isolated, and containers are also portable between machines. Containers, as I mentioned, allow potential multiple instances of services to easily be spooled up. So you could potentially have the same container in running in different configurations. And also containers allow for individual services to be pieced together like building blocks for a larger application. Finally, containers can help us to decouple our applications from the underlying infrastructure. So what this presentation won't tell you, so we're going to go through a lot of steps, but we're not going to go through all the low-level Docker details. These are quite well documented. I've provided a lot of helpful links at the end of the presentation as well. But this presentation is intended to give you some high-level technical details and some real actual getting started examples on our platform. So why is Variscite talking about Docker? Well, this presentation is going to focus on two main use cases. Host-based containers, not that host, but we're thinking of like a build machine, usually that you're cross-compiling your code on. That's what we mean when we say a host container, so a Docker container running on the host machine. And then a device-based container, so embedded device, in our case, our VAR-SOM or Dart platform on our Symfony board. So we're going to dive into the use cases and how we can use Docker and why we should use Docker on these in these particular use cases. So next, we're going to move on to some Docker basics. So we're going to start with Hello World. That's the best example to start with. All these examples that were run on the host side were run on my Ubuntu 22.04 machine, and I had an internet connection. That's the basic requirements if you wanted to kind of follow this later. Docker does run on other platforms though as well, worth mentioning. So we're going to start with a simple Hello World, which Docker includes essentially to make sure that you've installed Docker correctly. So I'm going to start by installing Docker. This is going to vary based on your Linux distribution, but in Ubuntu it's pretty simple, apt-get. Then I'm actually going to call a Docker command, Docker run hello world. And what's going to happen is it's going to look for this container, and if it doesn't find it locally, it's going to go pull it from what's called a Docker registry, which we'll talk a little bit about later. But for now, it pulls it, and we can see a hello from Docker, and we see a message. It says that our installation is working correctly. So let's try something similar to Hello World, but a little more customized. Busybox, you might be familiar with Busybox. It's a command line utility set. It's typically used on embedded Linux, but there's actually a Docker container that runs Busybox. So we're going to call the Docker run to run the Busybox container, and we're actually going to pass it an echo hello from Busybox. So it's going to do the same thing, pull the container, then we're going to run it, and we're going to see that it's actually piping the command out of the container. So what just happened, just a little diagram here, I didn't have Busybox installed on my machine. It was actually in a Docker container, but because I had Docker installed, I could run the container and I could pass a command to it. So there are tons of existing Docker service containers available on Docker's registry publicly. And these are just a couple of popular ones that I chose to display here, like Ubuntu and Python and Alpine, but there are many out there that you can just grab right off the internet. So next, just talk a little bit about the anatomy of containers. So we showed just like running Hello World, running Busybox, but we're going to kind of talk about how we can build up a container as we build towards a demo presentation later. So just kind of high level, we typically start with a Dockerfile. This is kind of like a list of instructions, and a list of instructions on how to build our container. We then run Docker build against that, which is actually going to construct our container. It's going to follow our instructions to wrap the different applications and things that we need inside our container, depending on our application. Once we have that container image, we can then do Docker run, like you saw with Hello World, and we can run the application and deploy the app. So Docker files, like I said, Docker files can be thought of a list of instructions or a script indicating to Docker how to compose the components of the container. Most Docker files rely on some base container of which they start from. So for example, like Alpine Linux is very popular, or Ubuntu. So a container will kind of essentially inherit a base and then add extra things on top of it that it needs for that specific application. So we're going to show composing a very simple container with a Docker file and a shell script. So this is essentially equivalent to what we did with kind of Hello World and Busybox, but instead we're just running just a Linux container or a Busybox container still, but we're packaging the shell script into the container. So we're making a custom container. So on the left we have our Docker file. We start off from Busybox, so that says this is our starting point. Start from a Busybox container and build on top of it. We then set a work directory within the container, and we copy our script into the container. Finally, we set a command that's going to run when the container runs. And you can see on the right, our simple script that's being copied in just says, hello, Variscite. So now we can, assuming we're in the same directory where we have that Docker file and that shell script, we can actually build this. So we can say Docker build dot for the current directory, -t to tag it, like a label that we can reference. We're just going to call it test app. And you can actually see it goes through all these steps of actually following through our Docker file to construct the container. After we've successfully built it, we can do Docker run test app, and we get the output hello Variscite. So now that I've kind of showed you how basic Docker containers can be created, let's talk about host-based containers and what I mean by that. So again, hosts, we're talking about development hosts, typically where you're cross-compiling your code as a software engineer. The issue is compiling software is complicated. There's many dependencies required on the host side, libraries, tools, etc. Often we aren't even sure which versions we should be using. As a developer, team size increases, the reproducibility of code also becomes a concern. And if we think about longevity of our machine and being able to produce code, I mean, many engineers probably know about, like, there's an old computer somewhere in the closet that's the only remaining machine that can compile an older version of code. So these are obviously some challenges that we have. Let's talk about, for example, like building some of Variscite's Yocto releases. Just looking at our wiki here, one of the releases from our IMX8 platform, you can see there's 2 Kirkstone releases, a Hardknott, a Dunfell, and a Zeus. These are all major releases of Yocto. They're all running different versions of the Linux kernel, technically have different requirements for build. I mean, on our wiki, with all our builds, we have a list of instructions, and one of the first instructions is, run apt-get essentially, to make sure you have all these packages. But if you're running a different version of Ubuntu, like it might be supported by that base Yocto build, but you are using, different tools and libraries. Just looking here at like some of the GCC packages between 20.04 and 22.04, there's different versions of GCC. So not only is it a question of can you build it, but like I said, reproducibility, like consistent building becomes a problem too. So let's see the problem even more. So this is a real example where I'm building Yocto Hardknott release on my Ubuntu 22.04 machine. So I just went with a pure Pocky build for simplicity here with QEMU x86-64. So I start by just cloning Pocky at Hardknott, run the typical Yocto setup script, and bitbake core image minimal. Right away, we get a warning that says that our host distribution, my machine, Ubuntu 22.04, has not been validated with Hardknott. And it's warning me it could experience build failures. And sure enough, I do experience a build failure. That doesn't mean it's impossible to build this on this platform, but at least out of the box with what's installed on my machine, it's failing. So what went wrong? I mean, some kind of environment or dependency issue. And this can be a problem, especially when you have to build different versions of software on the same machine. So what's a potential solution here with Docker? Well, host containers. We could use Docker on our host, and we could make a container that encapsulates our development environment. Since a container could contain all needed dependencies and it's portable, we can easily deploy this container to multiple machines running different versions of the host operating system. So this means, for example, using the same container, an engineer running Ubuntu 16.04 on their host would be able to run the identical container environment as another person running Ubuntu 22.04. So, the Ubuntu 16.04 engineer could potentially produce very new code, and the Ubuntu 22.04 engineer could produce very old code because they'd be using a single container with a unified environment. So with our example, we could build Yocto within Docker. So create a container that contains all the Yocto build dependencies. We'd start with a compatible base container with a version of Ubuntu that matched a system that was compatible with our Yocto version. So like with Hardknott 20.04, for example. Once we create the container, we could preserve it to utilize it whenever we need to build this version of software, even if the base dependencies are now obsolete. And this helps to future-proof our build environment. Now, note here that there's additional work that you might need to do on both the Docker and Yocto side in this example to truly future-proof it, such as caching Yocto downloads and storing the container image somehow. So Variscite has a solution for this already, which is our Docker build environment. We've created an existing Docker container that is targeted at all our building all our major software releases. So just think about this. We're not just talking about Yocto here, because we have Android releases, Debian releases, boot to Qt. All of these have different tools and dependencies. And if you're an engineer and setting up your machine, or multiple engineers consistently to build all these, could be a challenge. That's why we've provided our build environment container where you can build all these major releases. So let's use that container. Let's use that Docker build environment container. Again, same configuration with Yocto Hardknott. So this time at the beginning, I'm actually invoking a script that's going to run our container. Now, we have a wiki that has all the instructions about how to run the containers in different configurations. And I'm not going to go through all that now, but I do have a link at the end to that wiki article. So we're going to launch the Variscite container, and right away we see the terminal text changes, which is indicating we're actually running an interactive terminal inside a Docker container. We kind of do the same steps: clone the repository, Yocto source open embedded init build environment, and then pip8 core image minimal. Some short time later then, we actually successfully built the image. We did not get the same failure this time. So you can see, using my same machine that previously failed the build, I was able to now build the Yocto image by building inside the container. So now that we've talked about the host side of things, I want to talk about the embedded device side of things. So the second major issue in embedded design is embedded application issues. So just like our host side, Linux-based embedded software has lots of dependencies also. Oftentimes, these can be harder to install or provision. We might not be able to just simply apt-get some package. And even if we can, even if we're running, for example, our Variscite Docker release, what if we need a specific version? We could have a legacy device with older software kernel, which might make it difficult to run newer versions of software. I mean, we certainly encourage, as we maintain our releases and we push new updates for customers to update to the latest, but we understand that's not always possible. So using something like Docker could allow you to run things within that environment and still run them in a kind of a legacy BSP environment. Additionally, applications engineers might be unfamiliar with BSP environments like Yocto. So encapsulating everything in Docker, puts all the application components right together. So let's consider this with an example design. So this is just a simple example I made up with a flashing LED. Everyone likes flashing LEDs. So on our Symphony development platform with a Varsom MX93, so we have a general purpose LED on board connected to a GPIO. And I want to be able to control this with libgpiod. That's a user space interface to GPIOs in Linux. But I want to use the Python binding. So there's actually a Python library because I want to write a Python script that's going to be able to control this LED. And it's going to do so when it gets a command. It's going to run like a daemon and get a command from a local socket from another app telling it to turn on and off. That other app, in this case, I want to be a Node.js server, which is going to listen, open essentially a web server, listen for an HTTP request on, LED off, and then it's going to pipe the command down ultimately to turn the LED on and off. So potential issues. So our design requires multiple software components: Python, libgpiod library, Node.js, application code. How do we install these? Moreover, how do we install the right specific versions? Well, we could do this by containerizing it. So we could build our application within a Docker container. We could wrap all these components into an image. This would also freeze components at specific versions. By containerizing, we also create a portable environment, which could potentially run across multiple underlying platforms. So we're going to dive into the source codes of this component, this design. But before I do, I just want to kind of hit some of the files that we're going to be talking about and what we're going to see, because there's a bunch of files. We have a Dockerfile, which is the list of instructions on how to build this container. Make files just allows us to run make to build this. LED control.py, so this is the Python daemon that's going to use libgpiod to control the LED and listen on a Unix domain socket. And then we have our Node.js components, package.json and server.js. So these are going to define our Node.js server and what it's going to do. It's it's going to list when it's going to listen on for an HTTP request, and then it's going to write to a Unix domain socket locally. And then finally, there's just a simple wrapper script, start demo services.sh, just ensures everything starts up when we start the container. So now let's go through the source code here. So we're going to start with the Docker file here. So kind of like we saw before with the hello Variscite script, we're going to start from a base here. We're going to start from a Node.js Linux Alpine base. Set a work directory. We're going to copy in components and install components for Node.js. So this is building our container up. We're going to build up Python. We want Python on here. We also want a utility called SoCat, which is just kind of like a command line interface to a Unix domain socket that's going to allow Node.js to easily write to our socket. Then we install Python library libgpiod. And finally, we're going to copy all the contents in our directory into our container. So that's all those files, all the files we're going through now that I listed, they're going to be inside the container. And mainly the ones we care about are like the Python scripts and such. And finally, we also expose port 8080, and we have a start command, which is run our start demo services. So when the container starts, it's going to start up all the components inside it. So now let's look at the Python script. So I'm using the libgpiod bindings here. Just simple, opens a GPIO chip, gets a GPIO line, sets as an output. Then we have some Unix domain socket code. This is just creating a socket basically that's going to listen on locally, because this is a daemon that needs to hear from another application. And we can see here it's actually just waiting for like an on command, and then when it does that, it's going to set a GPIO value. We have an active low LED, so it's going to set it low, and when it gets an off command, it's going to set it high, turn the LED off. Looking at our Node.js app here, so mainly on the left here is just describing our package. On the right here, we're actually going to do our HTTP listen for LED, listen at LED on essentially, and then we'll run SoCat to pipe an on command to our daemon. Same thing with LED off. So now let's actually try to deploy the application. So we're going to start by just running make, just invokes Docker build. Like before, Docker build current directory -t. So we're going to tag it with our username /demo app. And just to emphasize, now we're running on the board. You can see root at IMX93 varsom. So we're not running this on my computer anymore. And same thing, same like before, it goes through all the Dockerfile build instructions to build up this container. Now that we've built it, we can actually run it. So this command is going to be has a couple more things than our like hello world, but we're going to say docker run -p for port. So we're saying that actually the application is running on 8080 internally, but we're mapping it to port 49160. We do a -d, which says run in detached mode. So this is going to run in the background. It's not going to occupy my terminal. We don't have an interactive terminal like before. This is just running in the background. It's possible to actually break into the container and run commands, but we don't need to do that because everything's going to just run automatically. We also need to pass it a device. So our GPIO is a character device in Linux, and we need to pass that. Normally the container is going to be isolated, so we need to somehow pass that in, and we can do that with a -- device and pass the GPIO chip that has the line that we need. And finally, we're calling the root /demo app the user /demo app. That's the actual container that we want to run. And after we run all that, we get like an ID of the container that's actually running in the background. Again, this is all running on the board now. So we've shown all the source now. We've shown how we build the container up, how we run it. So let's actually see it run. So I took a video here, screen capture on my desktop while pulling up my board IP address at the LED on, LED off addresses. And at the same time, I have a video going of our Symfony board showing the LED coming on and off. So So I'm gonna play it now here. So I've brought up right here, this is a picture-in-picture view. So you'll want to watch down here. It's kind of hard because of the contrast, because we have these power LEDs that are already on, but this LED at the bottom is actually off. So we're gonna go to my board IP, the port, LED on. And we can see that the LED comes on and we get the response from Node.js. LED was turned on. Then we're gonna turn LED off. And we can see the LED here went off. And it's gonna repeat this one more time in case anyone missed it. There we go. And this demo code is available on GitHub. I put it on GitHub, and I have a link at the end of the presentation. So you could actually pull this yourself and follow. I have some instructions there and run it on our Varsom MX93 if you'd like. So next I want to talk about Variscite's Docker Advantage. So we've explained about how you can use Docker in an embedded software design, why you should use it. So why should you use it? Why should you use Variscite specifically? So as I mentioned before, Variscite has two major families of SoMs: the VarSOM family at the top and the Dart family, on the left, and the Dart family on the right. Each family has a slightly different mechanical form factor, with the Dart generally exposing more interfaces. And as is seen in this chart, and depending on the pin-mux options needed, the devices listed within each of these families are generally pin-to-pin compatible. So this allows for scaling the device within the family without redesigning the carrier board. That's a big advantage, because say you needed lower power, needed to go to a smaller device, you could scale down to that device. Or say you needed more processing power, or you needed a GPU that wasn't on the MX93, for example, you could scale up to our 8 family, like 8M plus. This is a huge advantage. So let's talk a little bit more about scalability. There's traditional definitions of scalability, like system scalability, which is usually the ability of a system to adapt and fit to specific problems. We have software scalability. Usually that's the ability of a system software to dynamically, manage an increased workload. But when Variscite's talking about scalability, we're talking again about design scalability, like the pin-to-pin example on the last slide. So that's the ability of a SOM to run the same application on the same carrier board, while potentially using different SOMs should run the same. So just looking at 3 of our SOMs here in the pin-to-pin compatible family, Varsom MX93, which is what the demo is run on, the Varsom AM62, which actually is running a Texas Instruments part, and then one of our other NXP Varsom MX8M Plus. These are all pin-to-pin compatible, and these all run Docker. These aren't the only ones that run Docker. There are basically all our SOMs run Docker, but with just looking at these 3, using what we showed with our Docker embedded application, we could potentially run the same container on each of these. So we've already designed a very scalable platform in terms of both hardware and software support, but by including Docker in our environment, we make our platform that much more scalable. So which of our software platforms actually run Docker runtime? And that's all 3 of our major Linux platforms, which is Yocto, Debian, and Ubuntu. All these releases can run Docker containers on the board. So now I want to talk a little bit about some advanced topics, just some things. We're not going to go too into depth with the advanced topics, but just to kind of hit on these items, because I think it would be missing out if I didn't from a Docker presentation. So the first advanced topic is container registries. So I mentioned a little bit about this when we were running like Docker Hello World, a Docker Busybox, a Docker Run Busybox. So a Docker registry can be thought of kind of like a repository. It's usually hosted on a server. There's a public Docker repository that's like the default one, but this repository holds built Docker container images. Registries can be used from public servers, but it's also possible to host your own private Docker registry. Some advantages of using registries are the ability to control where images are stored, so as well as the ability to tightly control the build and integration process of your containers. So you can build these on another machine, and then you're deploying them to their actual targets. There's also use cases here with like continuous integration, continuous test, as developers are updating the Docker containers, this is all being run and tested and built on the server, on the registry. So another advanced topic is container orchestration. So often an end application is composed of multiple container services. So container orchestration is the term often used to describe the coordination of running the multiple containers in order to produce a larger application. So for example, some kind of web application, maybe it could consist of 3 distinct containers, like a web server container, Apache container, a MySQL database container, and a PHP environment. So one of the ways that we can orchestrate containers too is something called Docker Compose. So this is from Docker. It's a tool for defining and running multi-container Docker applications. Docker Compose is a method of container orchestration, and it uses YAML files that allow for the starting of a multi-container service with a single command. So I'm not going to give examples in this case, it's very well documented, but just want to point people to it's something they could look into, as they're learning how to use Docker. So some helpful links here. As I mentioned, the first is the webinar demo source itself, so that if anyone wants to try this or review it more, you can go pull it right from GitHub. We've got the Docker documentation, very extensive documentation there. We have our Variscite guide for our Docker build environment, so that's our host-based build containers. And then we have our Variscite guide. This is for a specific release. Many of our wiki articles are tagged for specific releases. This is for our previous Kirkstone release for the MX93, but the guide will be similar among a lot of versions. This is actually how to run, how to use Docker on the platform, on the embedded platform. Then just a Node.js guide that I used to put together part of the demo app, the Node.js portion, and along with just some of the Python bindings for the libgpiod reference. So now we're going to open the floor up to questions. So let me look through here because a lot of questions have come in throughout the presentation. Someone asked, wouldn't it be possible to cross-build with Docker and deliver a pre-built image? That process, as shown, makes it more complicated to deliver for production. So yeah, so what we're showing here is kind of this is a basic development flow to show you how the containers work and how they can be used. But definitely there's considerations for how you provision this at production, and there's multiple ways to do that. Registries are one, but there's also ways to archive Docker containers, and this is an advanced topic. But there's a lot of documentation on it, and something you should look into then is cross-platform builds, because there are considerations on how to do this for embedded devices. We just don't have time to show them here today. Let's see. Yeah, so is it possible to run an application requires hardware access in Docker, for example, a video encoder? So yeah, like I showed, this was just a basic example, like with a character device, but you can give Docker access to underlying resources. You can run Docker actually in privilege mode, where it basically has access to everything, but by default it's isolated and you need to pass things down to it. But you can either make it run in privilege mode or pass individual things down into the Docker environment. So it is possible to use external hardware within Docker. Another question was, can Docker replace Linux update solutions like SW update? So, I mean, potentially it could be used as an update mechanism, because it might be in your application that you don't desire to update the entire BSP. You may still want a way to do that, but say that you're just pushing out, most of the time when you put out updates, you're not changing the underlying environment, you're just changing the application. In that case, you could potentially use Docker as a mechanism to do that. You might still want to use something like SW update to help coordinate that, right? But at least from a perspective of just updating your app, you could be, yes, using Docker to do that. There's another one. I would like to save my Docker container image so I can use it later without rebuilding. How can I achieve this? So Docker container images can, be archived to a tarball by using a Docker save command. This would allow reuse on the same platform without rebuild. Now, like I said, this is more complicated when you get into provisioning and multi-platform builds, and there's a lot of documentation on the subject. But from just the basic answer, yes, you can actually archive it to a tarball with a Docker command. What version of Docker runs on your embedded platform? So this depends on the specific release of our software. But for example, our latest software releases to date are now using Docker version 20.10.17. Does FreeRTOS support Docker or some form of other containers? So not that I know of. We're not doing that on our platform, at least. So this is specifically, the presentation here, talking about Linux-based Docker containers. So what is a performance penalty with Docker? So I don't have specific numbers on that, and that's going to be heavily application dependent, but Docker is going to be much more efficient than running your typical virtual machine, because that's what it was run, it was made to run specific applications. So you'll have to do some experimentation to get specific performance numbers on that. Oh, and someone asked, what operating system is the LED demo running on? We were using the Varsom MX93, was running our Yocto, our latest Yocto Langdale release, and we were running the Docker container within that environment. So that's all the time we have questions for today. I want to thank everyone for joining and point you to our website, variscite.com, as well as if you have any questions about any of this or our SoMs, please reach out to sales@variscite.com. Finally, I didn't talk about our customer portal, but we do have a customer portal where we offer free support, where you're actually getting access to the people that are designing all this. So any of our customers, we encourage to, if you have issues, please go to the customer portal to open a ticket there. Also, consult our Veriwiki at veriwiki.com. We have extensive documentation on all our SoMs and software there. And everything is open source here. It's all on GitHub. So I also encourage you to go to github.com/verigit. And I want to thank you very much, and have a great day.